Well, anyway, so I would like to talk about balanced virtual conditions today, which is the technical tool that is used in the presentation of balanced forcing in the book, and which is not avoidable really. So I have to explain virtual, and I have to explain balance. So let me start with a simple definition. So what is a virtual analytic set? Okay, let X be positive. A virtual analytic set is a subset of X is a pair Q tau, say that Q is a coset, tau is a Q name for an analytic subset of X, and Q for the tau subset of X is analytic, and Q times Q forces the tau F is equal to tau. Now I have to explain what the terms here mean, because it is open to interpretation to some extent. So X is a Polish space in the Riemann. You can reinterpret it in the Q extension, and then tau is supposed to be a subset of the reinterpretation of X. Okay, it's supposed to be an analytic set. What I really mean is that really I should say that tau is a name for a infinite binary sequence, which index you have some fixed universal analytic set, and you're just identifying the section of the universal analytic set. Okay, and this one, this last line says that the name is such that when you look at the cross product, then of course you can evaluate tau left according to the generic filter on the left, tau right on the generic filter on the right. Then you reinterpret those analytic sets in the Q times Q extension, and you get the same set. Okay. So anyway, the situation is like this. So we have two generic extensions. There are few generic extensions, but that's not all that relevant maybe. And you have one analytic set here, one analytic set here, and then we realize in this space that when you reinterpret in some larger generic extension, that they actually reinterpret to be the same set.
So that's the motivation, the main motivation for this definition, because it's like virtual classes for pinned equivalence.
Yeah. So virtual classes for analytic equivalence relations are just a special case.
Okay. So the motivation, like the kind of like the naive motivation, or like the motivation for a person who.
Yeah.
So that you want to have control over the common extension.
Yes. So let me just point out an example. I mean, there are many examples. We'll see many of them in a second. But the most common one is when you plot the cardinality of the ground model version of the Polish space X to countable, and you get the name for the set of Y in X to be omega, Y to be raised S of the ground model. Okay, this is a typical virtual analytic set. So what is it? Okay, so in the extension, the ground model version of X becomes countable. You can consider the set of all of its enumerations. Okay, and now this is of course an analytic subset of X to the omega. It's a native analytic subset of X to the omega, and it doesn't depend on the extension in which you evaluate it. Okay, so this is a typical virtual set. Okay, if you were maybe more careful about this, you want a virtual analytic set to be an equivalence class of pairs like this, where Q tau is equivalent to, let's say, R and sigma, if Q times R forces that tau is equal to sigma, okay, or something like that, okay. Well, anyway, so this is, we're going to see a bunch of virtual analytic sets later on. They are nothing special, okay. There's a proper class of these things, and they are kind of not in this generality. You can't really do much. Okay, so definition. So let's be an analytic forcing. And the virtual condition in P is just a virtual analytic subset P. Just a virtual subset P, and which is identified with its Boolean sum in the Boolean algebra defined by P. Okay, identified. So what it is that you're adding a countable, you're adding in some analytic set of conditions, and you're kind of looking at its sum, at its supremum. Okay, so an example. So you look at the countable maps from R2, okay, and a virtual condition ordered by extensions. And a virtual condition, one possible and let add be any map from R to 2. And you can view it as a virtual condition. Hey, so you can view it as a virtual condition because when you collapse its cardinality to omega, then it becomes a condition. And it doesn't matter which forcing extension you're taking, it's going to be the same condition every time. Okay, so when you study this case more carefully, you realize that P is really not countable maps from R to 2, because that would be that would not be an analytic forcing. What you have is P actually consists of enumerations of countable sets and of omega and then range and then maps from the range to 2. Okay, and so here what you have is you're taking the collapse of the cardinality of F, and you're taking the sort of all enumerations of the domain of F, and then map which is on range of those enumerations, which is F. Okay, so this is kind of a simple example. Another example would be at the C be equal to infinite subset of omega. Ordered by inclusion that we had last time, and let's let U be an ultrafilter, be a non-principal ultrafilter on omega. And now, in any extension, in any poset that collapses the cardinality of continuum to omega, you can consider the set of conditions P and P, say that P diagonalized. That means it consists P is an infinite set such that every set in U contains P modulo finite. Okay, and you look at it, and of course, in V this is an empty set. Okay, but when you go to a generic extension, it's not an empty set anymore. When you collapse the cardinality of U to LF0, it becomes a Borel set. Okay, and the Borel set doesn't depend in which generic extension. Right. So that what a virtual condition is, and a balanced virtual condition. So by the way, for balanced condition, for virtual conditions, you can define an ordering between them that makes sense. That makes sense. Okay, just the same way. But and I will sometimes just compare virtual conditions and specific conditions. But what are balanced virtual conditions? So definition a condition, a virtual condition P now is balanced if and again there's this amalgamation picture. Okay, if for every pair of generic extensions, mutual generic extensions at VG0, VG1, again, draw the picture because it makes everything clear, at least to me. So here is Q top, okay? And the condition is that if you have a generic filter on Q here, H substitute T here, H0, then you have H1 substitute Q in this part. And if you find any condition, so now you look at tau over H0, that's one condition, and you look at tau over H1. If you strengthen this thing to a condition E and you strengthen this to another condition E, which are in the respective ears of the diagram, so this would be E0 and E1, then there is a common order boundary. Okay. And this of course looks very, very similar to what I had on last time, and there's still the pathway has to be proved, and I'm not going to prove it. There's just there's some cheap forcing tricks in it. The process is balanced. The process is balanced. If an omega for every T, there exists balance. Vertical conversion. Okay. And so just recall the examples that I had on the board this time, like this one. This is a typical virtual condition, but if you want to balance it, you have to make the map total. Okay. If you look at this is not balanced if the map is still partial. Okay. Because you still have the uncertainty which way it's going to go on some ground points. Okay. But if you extend it to a total function, then the resulting virtual condition is balanced. Okay. And here, if I instead just stated that this was a filter, then this would be still a virtual condition. And if you want to balance it, you need to go to a okay. So this is the theorem, okay, and I'm going. This is how balance forcing is presented in the book, and the book is full of attempts to classify balanced virtual conditions. Okay, so normally balanced virtual conditions allow a classification. This is in fact still an open problem whether this is always true. What do I mean by classification? There's an actual equivalence relation, and you can and that equivalence relation has only set many constants. Okay, that's the normal situation. We haven't encountered any other situation. Okay, like here for this post set, all the balanced virtual conditions are just associated with total maps. So, okay. And in this case, all the virtual balanced virtual conditions are associated. It's nothing else, okay? In any given case, it's not true that in any, it's not true in any given case, but in most cases, we have sensible classification and of balanced virtual conditions, and in some cases we don't, but we still know that there's only so many. Okay, so now let me try to prove the theorem that had more last time, because I think it's an interesting theorem. So in balanced extensions, of the solving example, there is no that family is a family of infinite subsets of omega, which are pairwise disjoint, and it's maximal with respect to inclusion, and it should be infinite, finite, trivial finite. So the proof of this. Let me just say, there's been an open problem for quite some time whether these mad families exist in the solving model itself. And but in fact, there's a simple proof that that works for all balanced extensions. Okay, and maybe okay, let's see how it works. So suppose for the contradiction, then so he is balanced, and he is a condition in P, and tau is a name in the solving model, so it's a phi plus tau is tau is in fact a name of tau is a set of rings. It's the set of pairs, a condition and a condition and a set, such that the condition forces the set to be in tau. You might also want to add to it the set of all pairs, condition and a set, such that the condition forces the set not to be in tau. Okay, that's okay. So in fact, tau is a set of radials, and it's well, so we can find it fix it in terms of that. Okay. So now let okay. Go into the model. Z, or any generic extension of V, which contains P and Z, it doesn't matter. But simplicity. Right, this one, find a balanced virtual condition. P inside this model, okay, inside this model. So for example, the ultra filter, okay, if you're looking at a parcel of omega module, okay, and then there's claim one, for every set A subset of omega in VPZ, bar P decides the membership of A and okay. And why is that? So this so why is it that it decides of A? Well, because if not, there would be conditions below it in the solving model. One of them decides it this way, the other one decides it that way. Okay, and but these conditions, they exist in generic extensions of VPZ, right? So there will be in VPZ both sets Q0, Q1, and the names say dot Q 0 and dot and Q0 1. Their respective names in the code set for conditions in capital P, which are stronger than the virtual condition, such that Q0 forces P0 forces A and tau, and Q1 would force P0, they're forced to be smaller. You can write it like this because we have an internal definition of what it means to force a set into tau. Okay? Otherwise, you wouldn't be able to write this because this thing is taking place W. Okay? We can write it like this in the forcing language of Q0 and P because we know that there is an internal definition of this expression. So we can rewrite it. Now, but then let P0 subset of Q0 and P1 subset of Q1 be mutually generic. And now look at the diagram that you get. Okay, so here is the Z. There's one VP0, there's one VP1, And there's P0, 0, and P1, 1. And they're smaller than this virtual condition bar P. So by the balance of the virtual condition, there's a common bound. But that common lower bound gives you a contradiction because it forces A to be both in tau and outside. Okay, so now you can see that this has nothing to do with any mad families. Okay, if we had a set of reals, if we had a name for a set of reals, okay, then the balanced virtual condition would decide how which reals from VPZ belong to it or not. Okay? All right, so well, let's handle so let A in VPZ let A be equal to the set of workers A such that the vertical condition forces A in R. Let's decide it. We can see it in VPZ again. This would be impossible if we didn't have the internal definition in the first place. Okay. Now A is not a mad family. A is just almost disjoint. Okay, you don't know if it's mad, but it's almost disjoint. Okay, so A is an almost disjoint family, but what you can do with an almost disjoint family, we can find an ultrafilter disjoint from it. Okay, a non-principal ultrafilter. Now what you can do, you can find in a generic extension, you can find a set which diagonalizes U. And then that set has finite intersection with every element of A. So there will have to be an element, there will have to be an element in tau, in the maximal almost disjoint family, which is presumably forced, which intersects. Okay, so there will have to be Q, which forces that a sigma diagonalizes the other one is U, theta, the subfield of omega has infinite intersection with theta. And there will be a P which is less than equal to P, such that P forces theta is. So there will be a post set Q, which forces all of these things. It forces it diagonalizes U, and then it finds some set which has finite intersection, which is infinite intersection with sigma, which is going to belong to tau, and of course it's going to be enforced by something. Now, so now let's E0 be one to the Q be mutually generated. Okay, I look into the check. Here is small d. It has A, it has U over U, and it has this balanced virtual condition. The extensions are mutually generic, and they have this they have sigma over G0, which diagonalizes U. Then they have tau, theta over G0, which has infinite intersection with that. And then they have P0, which is a condition which is this. And then P1. Now, you know, there's when you look at the intersection of this and that, and the intersection of this and that, these are two infinite sets which diagonalize the ultrafilter U. We proved last time that if they are in mutually generated extensions, they intersect. Okay. By bonds of this, G2 have a common lower bound. Okay. Now, if you look at the common lower bound, the common lower bound forces this one and that one into tau, and they you force this sigma theta over G0 and theta over G1 and tau, and these two have infinite intersection. Well, that is a contradiction. Well, you have to still observe that these two, it could happen in principle that they're the same, right? Then there wouldn't be a contradiction. Now, the family is supposed to be maximal almost disjoint, which certainly this is a problem, except in the case of these two. But they are not equal because one of them is in this model, the other one is. Okay. So, was I making sense? Is there? I mean, this is the time to ask questions, okay?
What is this tau clause slash D0?
You mean Jindrich?
Yes.
So this is the evaluation of the name theta.
Okay, okay.
So that you want to, this is the notation that I use, literature.
Okay, so theta is a name.
All right, so in particular, you can force an ultrafilter and in the generic extension to have no maximal or disjoint family. Okay, but you can do many other things, okay, whatever balance you do, you will not get that. All right, so I have still 15 minutes. I will want to tell you about how you can stratify balanced forcing to get some very detailed independence results, okay? Because balanced forcing allows essentially endless levels of stratification and try my uh, maybe look into sure I make the right. So if so my B I'll be a sportsman and not here okay. When strengthen the notion of balance, one can strengthen balance by weakening the mutual genericity demand on the diagram. Okay, weakening so the diagram looks like this. B, this is part B, and there are two generic extensions here. One, and in the balance definition, we required the two to be mutually generic, and that was actually a good reason for it when you look at how the proofs go. Mutual genericity is somehow the free. So, but you could try to strengthen it, and there are many variations. Okay, they're not all that simple to state always. Okay, so one way, one example. We got the demand rate was only zero intersecting one. Then another possibility is to demand something about algebraic sets, so there's an interesting connection with algebraicity that I don't have time. So you could require the, if you have an algebraic, if you have a set here, and you look at its algebraic envelope and you calculate it in this model or that model, you get the same sets. And so, okay, there are many options, okay? Other options that actually are very useful in situations. One can also permit for example, you could permit a diagram which has 3 years. You could permit the diagram which has 3 years, and let's say their pairwise mutually generic. Okay. And the demand would be that whenever you have a condition in this year, that year, in that year, or in that year, they're compatible. Okay. Maybe you require these two to be mutually generic, these two to be mutually generic, and these two to be mutually generic, but you don't require all three mutually generic, for example. Okay. Good. And then there is just endless scale of options for you generate. Okay. It has to, these diagrams that you're drawing, they have to satisfy certain opposite properties. I don't want to wait this. Let me show you what we can achieve. This leads to some. This leads to the notion of placidity.
So can I ask?
Yeah.
So for the original definition,
Yeah.
then the product forcing is the pullback, the push out.
Yeah.
These two forcings, right?
That's right.
So this is like the smallest.
That's.
And this would be like strong amalgamation.
Yeah.
Which is like a weaker condition.
That's right. You know, as you're weakening this demand and mutual genericity, you get all kinds of diagrams that are somewhat unpredictable from forcing. Okay, the product has the advantage that the product is right in your face, and you can analyze it. But for these diagrams, it's not always that simple. But let me show you what we can do with this. Okay, so there's a simple, well, in retrospect, a simple theorem. We were very happy when we achieved it 5 years ago, but in fact, in retrospect, it's very simple. Theorem. There is a balanced extension down the room. So the model in which there's a hammer basis for R over 2, but no algebraicity transcendent spaces. And this is a very simple theorem in retrospect. So from that Hamel basis, or really any space, you can get it without introducing it. Okay. And the point is that the amalgamation diagrams for these things are easy to get than the amalgamation diagrams for these things. Okay. So there is an interesting open question. Of course, if you have a Hamel basis, then you have many permutations, many polymorphisms R as a vector space over Q. But we don't know how to introduce them, and the same thing for this transcendent spaces. And we don't know how to get an automorphism of vector space and not introduce a automorphism of the field. So it's somewhat unclear. But anyway, let me respond to the both of P. I mean, I don't have enough time to show you every detail of this group, but the both side is not. Linearly independent they're linearly independent. Okay, and they are ordered by extension. The point is, the main thing is that the amalgamation diagram can be, the diagram can be amalgamated as soon as the 2 years are distributed over B. Okay. So the diagram can be amalgamated. VP0 intersection VP1 is equal to B. Okay. Let me show you why that is the case. So that you have a connection P in your poster, and what is the balanced virtual condition? What is the balanced virtual condition?
Basis.
Yeah, Hamel basis that makes sense. P. I mean, it works. Okay. It doesn't, it's in fact a very intuitive. These balanced conditions look like an abstract thing. In fact, they're very, very intuitive thing which have immediate semantics to them. Okay, I mean, it's not just some sort of forcing calculus. They have clear semantics. Okay, and so RP is just Hamel basis in fact. Okay. Now, so now you extend it. Now you extend it P0 and P1, which are linearly independent sets here and there, which extend RP. And then you show that P0 union P1 is independent. Why not? Why would they not be? Because if there was a non-trivial linear combination which gives 0, then you could separate the linear combination into 2 sides of the equation, such that one of them contains only refers only elements of P0, the other one only elements of P1, and they will be So that would mean that the result of the equation is in VG0 intersection VG1. But if VG0 intersection VG1 is equal to V, so then the result is in V, and that would contradict the fact that you started from this. Okay, so this there's a little bit that has to be added to it, but okay. And then now let me tell you roughly how the transcendent space is excluded. So you have to learn how to exclude the transcendent spaces. And the transcendent spaces has the problem that its amalgamation diagrams don't work. So to exclude consider the following diagram. Consider a generated couple of variables. Such that the dot product R0, R1 is here to is. Okay. It doesn't matter what this thing is, as long as it's not zero. Okay. I generate couple. What does it mean? Just added microenforcing. You look at the set of all couples like this, they form a closed subset of R to the 4. So it's Polish force with non-empty open subsets of that will give you a generic couple. You look at R0 R1 here in this year, and you look at R2 R3 in this year. Okay. And what happens is you have to verify, which takes a little bit of time, but not all that much. These two are mutually generic. This over the one. These two are mutually congeneric. Congeneric reals as well. Then the key part is the VG0 and VG1. The intersection of these two is equal to V. That's not so easy, okay? Why is it not so easy? Because this thing is not these four are not mutually generic because they satisfy this. But it actually is the case of this intersection. Okay, and then what you're getting is a free pair on the left, a free pair on the right, such that they satisfy non-trivial algebraic equation, and that will make it impossible to have a basis in the extension, because this pair will okay, somehow you will be able to amalgamate a diagram with conditions in the P, and you will introduce some algebraic identity among the elements of the basis that give you these two, and that give you these two. Okay? In fact, this argument is quite soft. It is not necessary to have exactly this equation. Many other. Well, anyway, so I think my time is completely over. So, so this.
cube. Right, so if there are no questions, then.
Oh, yeah, I have a small question. In the main theorem about non-existence of this mad family, we always assume that there is a strongly inaccessible cardinal, right?
Yeah, this is used all over the place. I'm not stressing it, but it is used all over the place. Let me show you one key place where it's used. So we got this model UPT. We got this bonds condition. We got this set A, which was shadow family. And we got this one. So one thing that we needed to do, we needed to be able to diagonalize the filter, which could be done without collapsing kernels, okay, by CCC set. But then I needed to produce two mutually generating statements. Okay. But more than that, I needed to be able to actually realize the balanced virtual condition. Okay, so for example, if you want to I mean, in some cases, this is possible without collapsing kernels. Like if the balanced virtual condition is if we're looking at the post of omega modulo finite, the balanced condition is a ultra filter, and we just need to diagonalize it. This is possible to do with CCC forcing. You don't have to collapse anything. Okay, it's still fine. Then you also need to know that there will be a condition which forces a condition in the post P which forces something into the math family. Okay? And that forcing you need to be able to duplicate it to take a product forcing of the two. Okay. Now, if you don't want to use the inaccessible cardinal, with the inaccessible cardinal will be perfect, because we know that this model, is essentially countable. The post sets that generate these ears, they are countable, and from outside from the model, viewing it from the model W, we know that we can find it for the extensions. Now, if you want to eliminate the inaccessible cardinal somehow from this argument, then you have to be very specific. Okay? You have to say somehow that your balanced post set is such that the balanced conditions you don't need to collapse cardinals and so on. Okay, there is a number of things that you have to do. Okay, and I'm not saying it is impossible. In many situations, it is possible. Okay? But there are situations in which it's impossible. Okay? In which you can actually show that some independence results that you obtain in this way really need an inaccessible cardinal. Okay? About this particular one, I'm not going to do. If you have to have a non-principal ultra filter and no math family, maybe you don't need it. Okay? Maybe you don't.